I truly believe, honestly, that great engineers, they kind of grow up from really curious children, sorry. And I grabbed this article from the internet. There was a guy who tried to figure out how many actual megabytes are written on a compact disc. You know, these standard optical things. This is the picture of 650 megabytes compact disc. And the question is, how do you think how many actual megabytes are written there? Like, anybody knows? No? 650 megabytes. So obviously not 650, but how much? The answer is that this guy actually calculated. He counted every dot on the surface, and he claims there is about 900 megabytes being written of raw data on an average compact disk. The reason why is that you need to have some extra data to tolerate an imperfectness of the disk surface, and also to tolerate the scratches on the surface. I mean, it's quite bad if you can't read your disks. And the set of algorithms that is responsible for that is called, in general, erasure coding algorithms, and there is the most widely used one called Reed-Solomon. Reed-Solomon codes. So this set of algorithms was invented more than 60 years ago, and back then even computers were not really a thing. It was firstly used only a few years after, when NASA launched their first probes, these Voyagers, which are now over 21 billion kilometers away, and we are still able to effectively communicate with those things over 20 billion kilometers. Originally, NASA didn't put any erasure coding algorithms into the communication protocol, but after a few years, they had to do that because the amount of transmission errors increased so much they were not effectively able to talk to the probes. So how this erasure coding algorithms actually work is that after every block of data, you have some you have some other block of so-called parity data that helps you or allows you to reconstruct the original message if the parts of the original message are lost. So for instance, this is the example how we actually split the data when you upload it to our cloud, how we would split it if you uploaded it to our cloud. But AWS and Google actually, well, maybe not officially, but people over the internet say that basically AWS does roughly the same. So how it works, you have your string, you split it into some number of data chunks. In our case, we usually split it into 3 chunks, and then you generate another 3 of so-called parity data. The size of the chunks is like they're all of the same size, so you're technically duplicating the amount of data. And the configuration, the number of data chunks and parity chunks could be different, but we usually use 3 plus 3. The general rule is that you can lose up to the amount of parity chunks that you have. So you can lose effectively any 3 of these chunks, and you will still be able to reconstruct the original message. Next slide, please. Yeah, so technically and hardware-wise, what actually happens behind our curtains is that we have this so-called, we call it a unit of scale. This is just a set of servers that we consider our unit of scale. It's 3 servers and 3 JBots connected to the servers. Every JBot holds up to 102 physical drives, and we use 18 terabytes Western Digital drives. So we are able to hold up to 5.4 petabytes of data in our unit of scale. But if you remember, we duplicate the amount of data that our customers upload, so we are able to effectively store up to roughly up to 2.7 petabytes of customers' data within this unit. So every unit of scale is kind of independent. It has its own database. We use Mongo. cluster, so every server runs its own node of Mongo cluster. We need the database to store the actual metadata about files, like their names and customers' headers and our internal stuff. And also, every unit of scale run a set of our Go microservices that are responsible for the actual magic there and for the API as well. So performance-wise, we consider ourselves quite effective. Our Go microservices mostly consume nothing. Go is extremely efficient, and we utilize roughly about 0.5 or 1% of memory. I mean, our microservices utilize roughly 1% of server's memory. We have 32 gigs of memory on every server. And CPU-wise, I have never seen more than 5-7 cores being occupied on every server. We have 24 cores per server, so, and 2 threads per server. But again, the CPU utilization is quite a complicated topic on its own, because what the CPU utilization mostly is just I/O wait, because our processes are mostly waiting for the drives to finish the read or write operation. So yeah. Well, this is the physical hardware. This is the JBot. Tommi is a big fan of this thing. And physically, we hold our stuff here in Tallinn. We have our stuff in Greenergy data center currently. These are the official pictures of the data center, and this is the official picture of Tommi holding the beasts in the data center. But because of some geopolitical reasons that you might be aware of, we are also planning to open a new data center. Oh, not the data center, but to move our stuff and open a new location in Netherlands at the beginning next year. So, yeah, we try to be as minimalistic as possible. Performance is very important for us, and we are also quite a small team, especially in comparison to our competitors. So we don't have that many dependencies. Actually, our Go microservices, the MongoDB, and that's it. And our Go microservices are self-containing small binaries of 15 megabytes in size with 0 dependencies. In theory, we could run them in so-called Scratch Docker containers, because they are statically linked and they don't even depend on config files. We configure them through environment variables with systemd. And Tommi told me that I have to mention this WireGuard. That's what we use for our internal networking. And he said that I should say that WireGuard is for cool kids. And yeah, obviously we encrypt our stuff with Linux level encryption. We use this Lux for drives encryption when we mount them. Oh, now it works. So, API-wise, so in front of our hardware, there is the API that our customers use. We have chosen S3 because it's widely used. Everybody knows how to use S3, and there is a bunch of existing software that is capable of doing stuff with S3. Backends, for instance, actually, we use ourselves for logs. We have, a few months ago, we finished the project of migration our Elasticsearch onto Storadera Rails. So we moved from Elasticsearch cluster to our on-premise Elasticsearch instance, and now we are saving roughly 6,000 euros per year by just doing that. And we keep the logs are being backed up as snapshots onto Storadera servers as well. So yeah, we back up Storadera to Storadera, but this is just for logs. So S3 endpoints, we obviously don't implement everything that AWS has in terms of S3. We implement roughly, it depends on how to count, but maybe 30% of all the endpoints. But we believe that we implement roughly 95% of stuff that an average S3 user actually needs. So generally speaking, we have obviously everything that you need for object storage, and we have versioning and immutability support on top of that. What we don't have at the moment is kind of proper permission system. So no IAM roles or anything like that. You just have a general account with general permission, but this is the next thing planned for the next year. And yeah, we have 100 gigs of object size limit, object size limit, but it's basically limited by amount of time that we need to recalculate the hash. So when you complete your multi-part upload, we have to recalculate the hash, and it takes some time, and we decided to limit it with some reasonable amount. So performance-wise, so we are, as I said, quite efficient and happy with the current results, even though there is lots of room for improvements. We see still every day customers upload up to 7.5 million objects to our cloud. We've seen numbers like 200-300 requests per second, API-wise, and our internal calls, of course, the numbers are quite higher on every customer call. Behind every customer call, there is a bunch of internal stuff going on, and internally we have maybe up to 5,000 requests per second. And yeah, we have some problems as well. As I said, we are a small team with limited capacity, and we've seen troubles with our customers who use Veeam. You might be familiar with this thing. So this software actually creates really a lot of really small, from our point of view, objects, maybe between a few kilobytes and few megabytes in size. And when one of our customers created 300 million objects, everything became extremely slow. Well, mostly because, as I said, we store our stuff, meta information in the database. And some of the S3 endpoints require us to aggregate data on the fly. This is the part of official AWS documentation. It's an example how you list objects and folders, and there is no actual folders in S3. The folders are just part of the object names with the delimiter that you provide along with every request. So every request could contain any kind of a delimiter. It could be slash or backslash or dot or even an A character. So we can't pre-calculate this stuff. We have to do it on the fly, and this is extremely computation heavy. So just for you to know, if you have 300 million objects in the file, the listing will be slow. That's basically it from hardware and software part. And now Tommi will tell you how the company started and what's the business model behind it, like how expensive it actually is to use us. So thank you, Tommi. The stage is yours.
Thank you, Dmitrii.
Oh, you don't.
Can you hear me well? So Dmitrii is our storage backend head, engineer, senior, and everything. And everybody in our engineering team are DevOps. So this is why we're here. But yeah, I will go back in time a bit. 6 years ago, I decided to do a simple computer backup service. And I thought I will use AWS S3, of course. But it turned out it's too expensive to use it, and actually it will, this business will not be profitable. So I considered also some open source software, but they required lots of hardware resources, and actually, for example, OpenStack Swift required 1 gigabyte of memory for every terabyte stored, and increasing memory in server is exponentially expensive if you go big with this big JPod. So as an engineer, I thought that maybe I could do it myself. And I started prototyping the software, and soon enough, I had a prototype. But as Dmitrii mentioned, there is this Reed-Solomon algorithm. I decided to use it because it requires actually less hard disk space than just duplicating data 3 or 4 times, and still gets the durability. The question was, is it like really CPU intensive to do these parity calculations? And everybody at the time in the internet said that no, you can't run real-time like hot storage with this algorithm. But yeah, like with prototyping and running on really old physical Celerons, it turned out it's really possible, and I decided to drop the backup part and concentrate only the storage. To do this, our goal was to make really cost-effective storage. So we have to care about performance. And this is a graph of our CPU load. In Linux, processor can be in 4 states: user, system, idle, and I/O wait. Green is idle, red is I/O wait. So it may look like CPU is quite busy, but actually what this I/O wait state means is that the CPU has nothing to do, and one of the threads is waiting for I/O. So it's basically idle. And this is why this is one example how we actually need to dig deeper than just looking at Linux load, for example. Some facts about S3. So the acronym means Simple Storage Service. But spoiler alert, it's not that simple anymore. There is 97 endpoints total in this protocol. And it was one of first 3 AWS services launched in 2006. So Amazon actually thought it's a really important thing. It is XML based, but you shouldn't actually care too much, because typically you use it with many available S3 compatible applications, or you can use it with Amazon SDK. So this is the funny thing, that all S3 compatible storages can be used with AWS SDK. And we even use it for our internal testing SDK, so we're compatible. And this SDK is available in 12 languages as well. So S3 storage is good for many things. Like most obvious one that people think initially is backup, but you can use it from your application to store any data, like photos taken from application, just whatever is there. And also for machine learning data source, it's really good. And like I can't mention all of the cases. One thing can't be good for everything, and the S3 is actually not good for things that require granular random data access. And typically things are operating system, disk if it's on virtual environment or database. And for these cases, there are typically block storage services. In 2018, it was estimated all data centers use 200 terawatt hours power per year. And some may think using cloud is actually like contributing to use more power. But typically it's not the case because of scale. And in our case, hard disk is one of the big power consumer. And there's a funny thing that the hard disk size doesn't actually affect the power usage too much. For example, our 18 terabyte drives consume roughly 7 watts, and 1 terabyte drives consume 5+ watts. So it's quite similar. And we did a small case study comparing Storadera to Synology NAS device, a small one with smaller drives. And in this specific case, we actually were 5 times more energy efficient. Yeah. You probably have seen how complex is cloud pricing, different cloud services. And AWS S3 is no exception here. On the right, there is a part of S3 price list from AWS. It has, the basic cost is for storage, but there are additional fees that have different levels of price. Like download is the most known, but there are charges for if you list your files. This thing that Dmitrii talked about is a bit slow if it's hundreds and millions files. But the problem is, if you probably know, like if you plan to use something, you don't know how many times you're gonna list your files in a month. Like, is it 1,000 or 100 million times? And this can add up actually, in some cases, 10x the cost that you initially thought. So with Storadera, all this engineering and effort is put to make things simple. And yeah, this is our price list. And I can scroll it back for a second. This is AWS price list, part of it. And this is Storadera. So yeah, it's for making life simpler for engineers. Thank you.
Round of questions, Todinka.
How fast you can recover from, let's say, 2 hard disk failures? Like rebuilding the whole disk?
Yeah, so I don't have exact time for our internal recovery, but customers don't know it. So like we recently, in this summer, we moved to this new data center. Even physical moving of our hardware in like small chunks, customers didn't know that we moved to new data center. So we have put really a lot of effort to make it seamless to customer or the user.
Awesome.
Hey, thank you. Very cool. I have 2 questions. One is like DevOps related on the looks and the encryption on your side. And the second question is like a user encryption. Do you support a user to upload a public key so that I could encrypt data on my side and upload it already encrypted to you so that you don't know what I have there?
Mm-hmm. Thank you. So this is part of S3 protocol, and we haven't got to this specific feature yet. So this is planned for next year.
Okay, but the looks part, how do you, I mean, the DevOps problem, you know, the chicken and egg, how do you encrypt data looks on your side? So who kind of enters the password?
So at the moment, this is a manual process. So there's chicken and egg are like separated.
Thank you, and awesome to see such like low-level talks. Peter, question? Did I saw a hand? Yeah.
Thank you for the interesting talk. My question is about Go. What are your main learnings for using Go? For example, when you had to really crank that performance, or yeah, because we use Go as well, and I know that it's relatively new language. It's 13 years maybe on the industry, and sometimes, for example, there's a lack of packages if you want to do something versus Java or some other things. So, what were your main learnings about using Go?
Thank you. This is excellent question. So as I said, I started it 6 years ago. So actually, it didn't start as like a full-time job, as things often start as a side hobby. And actually, after starting this, I actually went to work in Bolt, and half a year I did nothing. And then after half a year, everything still worked immediately if I started again. And actually, as Dmitrii showed, there's this really high amount requests per second. So we even didn't like have to think about it for a very long time. So everything works really well. We haven't had many or maybe any trouble finding libraries because we don't depend on many things. So like common things are in this standard library already. And well, this has improved in years as well. So yeah.
I may add a few words to that.
Yeah.
So basically, for Storadera, Go was kind of an obvious choice, but for me, this is the third or maybe even the fourth company I worked for where company uses Go mainly. Go is actually, in my opinion, is a perfect language for almost any case. So dependencies-wise, what in average language your dependencies are like some kind of an implementation of HTTP protocol or maybe some low-level algorithms. But in Go, there is so many things already included into SDK, as Tommi mentioned. And also it is built around the idea that you don't actually need most of the dependencies. So it is not an object-oriented language. It has structures, but they are not like the same as standard OOP things. And if you are used to that, you kind of get used to that, and you don't need many dependencies actually. And performance-wise, Go has so many built-in tools for optimizations and performance optimizations that it's kind of really, really difficult to write slow code with Go, because you just write the performance profiler and you see immediately what your bottlenecks are. For instance, for me, myself, personally, it was a big discovery that switch over integers is actually several times faster than switch over strings, for instance. You never think about it, but it kind of makes sense because you have to compare one number or several numbers, what strings are. And there is lots of discoveries like that that you go through, but when you do, you kind of end up with a really performance-efficient code.
I can add one thing, surprising, that MongoDB driver actually does a lot of memory allocations, and it consumes lots of CPU time. Like percentage-wise, time-wise, like it's nothing.
Yeah, when we write our objects to the disks, we actually have done some work on memory allocation optimization, because when your customers upload something, these are new bytes that appear, and you have to write them into memory, obviously. And then another chunk of data comes, and you have to kind of garbage collect the previous memory and then allocate a new one. But with Go, you can actually easily avoid it with concept of sync pool or something, and reuse the same memory, and it actually affects your performance quite a lot.
But most of the time you actually don't need to performance optimize. Like you have to be really sure that you need it just to do it.
Okay, let's have a big round of applause for Tommi and Dmitrii.